Hello students. So in our chapter, which is in continuation system of particle and rotational motion, today we are going to study the principle of movements. I think you know the lever. It is a type of machine, and an ideal lever is essentially a massless rod pivoted at a point along its length. Means a lever is a rod such that it is balanced at some point on its length, or you can consider that point as its center of mass. If no of the force or no of the weight is acting at the two ends of the lever or the rod. So the point where the lever, the rod is pivoted is known as fulcrum. Figure shows a rod AB which is pivoted at a point known as fulcrum, as shown in the figure by the red triangle below the rod. By watching this figure, you can remember a game, seesaw game, which the children enjoy too much. What happens there when children are enjoying the seesaw game? Two children at the end of the road are sitting. One children is at end A, one child is at end A, and another child is at end B. Since both of the child has some weight, so the direction of their corresponding weights will be downward due to the gravitational attraction of force. So the weight direction will be downward towards the surface of the earth. So let us sketch the situation where the two forces are acting downwards at the end of the rod. See the figure number 2. A rod AB is pivoted at point O at a fulcrum, and a force F1 is acting downwards at point A, and F2 is acting at another end of the rod B. The end A of the rod is at distance d1 from the fulcrum, and end B of the rod is at distance d2 from the fulcrum. Both of the forces are parallel to each other and directing downwards. Here we are considering that at this moment, this lever AB, the rod AB, is at equilibrium with respect to the fulcrum. So, for the lever means the rod AB to be in equilibrium, that is the translatory equilibrium. We can say that R minus F1 minus F2 will be 0, where R is the reaction of the support at the fulcrum and it is directed opposite to the forces acting at the point A and B. The direction of the R is opposite to the F1 and F2. So for the translatory equilibrium of all of these three forces, F1, F2 and R, we can write here R minus F1 minus F2 equals to 0. So this is the translatory equilibrium condition. If we consider that the rod is in rotational equilibrium, then for the lever to be in rotational equilibrium, the moment of the forces with respect to the fulcrum must be in equilibrium. So we can write d1f1 minus d2f2 is equals to 0, where as we know the distance of force, perpendicular distance of force F1 from the fulcrum is d1 and perpendicular distance of force F2 from the fulcrum is d2. Generally we consider the anti-clockwise movement as positive as well as the clockwise movement as negative. Of course we can take opposite also. Depends what reference we are taking. Since the reaction force is acting on the support, so its movement with respect to the support will be 0 because it is acting at the support. If the force F1 is here as the load, then if F1 be the weight of the load to be lifted up, then D1 be the load arm. Similarly, if F2 be the effort to lift up the load, then D2 be the effort arm. So, for rotational equilibrium, D1F1 is equals to D2F2, or we can say load arm multiply load is equals to effort arm multiply effort. This equation is known as the principle of moments for a lever, is known as principle of moments for a lever, and the ratio F1 divided by F2 is known as mechanical advantage. In short, we can mention it by MA. It means mechanical advantage is equals to F1 upon F2 is equals to T2 upon D1. So if the effort arm is larger than the load arm, the mechanical advantage will be greater than 1. So effort arm is larger than load arm, then mechanical advantage is greater than 1. It means a small effort is required to lift up a heavy load in this condition. So that's all for today. We will continue with the next topic. Till then, good day.